two things that we already said that I should highlight right away. So what we said here is that the spring force depends on displacement. That implies that if I have a larger displacement, I'm going to have, right? I'm going to have a larger pull by the spring. Now, you could say, yeah, but what if I distort the spring so much that the spring can't do that? Well, that doesn't count. We have to assume that it's a proper working spring. So if I have a larger displacement, I'm clearly going to have a larger pull by the spring. If I have a smaller one, then of course I'm going to have a smaller force here applied by the spring. And I mean, of course this makes sense, right? A bigger X versus a smaller X, this has to be proportional like this. And that makes physical sense. The negative sign, right? This is the big one. And you're going to see that this is going to be an issue in the modeling project because the sign, you have to be careful how you define your sign system here. The negative sign indicates that F of spring is always opposite. Always opposite in the direction away from the equilibrium point. So if it's moving towards, if the cart's already moving towards the equilibrium point, then that's not the case. It's always about moving away from the equilibrium point. So the other thing that we should talk about here, separately, is the spring constant. And it turns out that students really find that the spring constant, measuring it, is where many people actually make a lot of experimental, errors. Is for some reason, people really struggle with measuring the spring constant. And we'll talk about that in lab, how to actually do that. So here we go. So what does the spring constant tell us? This proportionality constant tells us about the stiffness of the spring. It's about the stiffness of the spring. So what do I mean by that? Well, if I have a large spring constant, what it does here is that we call it a stiff spring, but what it means here is that it's hard to either compress or stretch. And when this is the case, this is what we call a stiff spring. So if it's hard to compress or expand or stretch, excuse me, it's a stiff spring. However, if I have a small spring constant, what you're going to find here is that this guy is going to be what? It's easy to to do that. And so therefore, you're going to have what we call a soft spring. So so think about your bed. Most beds are spring beds. Would you want a stiff spring or would you want a soft spring? Most people prefer a soft spring. You don't want a spring constant so large that as soon as you lay on the bed, it feels like you're laying on concrete. Most people prefer soft beds. So therefore, the K value should be smaller here. And what about your car? Well, if you think about the shocks in your car, that's a spring constant. Would you want your car to be too soft? If it's too soft, what actually happens? You might hit the ground as you bump up or down. But if it's too stiff, it could be, quite jarring when you're actually, you stop all of a sudden. By the way, the same thing happens with bikes, right? If you look at I know that most bikes now have spring systems attached to them, but if you look at, let's say, like road bikes that typically do not have spring systems, there are bikes like, let's say, carbon, for example. Carbon is a very stiff material. So a carbon frame, if I remember correctly, has a very large spring constant. But if you take a steel bike, the steel bike has a much lower spring constant, so it actually feels softer. And the question is, what is it that you like? But that's what we mean by a spring constant right here. So then when I look at the units of the spring constant, okay, so if I look at the units of K, then I use Hooke's law. So I know that Hooke's law tells me unit-wise, it must look like this. So then this tells me here is that a spring constant is then going to be, which then is a Newton meter. And so what does this spring constant when it says a Newton meter? Well, so units of Newton meter imply how much force is required to stretch a spring by 1 meter. So let's say something like this here. So one example may be, what happens as an example, let's say that I have K equal to 100 newtons per meter. Well, picture-wise, what I imagine here is that I have a spring. And then what I do here is that I look at this spring, and right now, this is in a relaxed state. And that implies that the spring force is 0. Because why? This is the equilibrium point. And the equilibrium point tells me that if there's no displacement from the equilibrium, the spring force is 0. So now what I'm going to do here is that I'm going to imagine that I'm going to stretch the spring. How do I stretch the spring? From the equilibrium point. So now I take this spring and I'm going to stretch it. How much? I'm going to stretch it a distance of 1 meter. So how much force did I have to apply to stretch this spring 1 meter? I had to apply a force of 100 newtons. And there's a lot of details. I mean, how we actually get the spring constant. You can't get the spring constant by one measurement. It's an approximation. Typically, you want to look at some of these other things. By the way, just as a really interesting point, or interesting aside, buildings act like springs. So as an example here, imagine, so I know this value because I read it about several years ago. If you look at the Sears Tower, right? You look at the Sears Tower in Chicago, right? There's a reason why they call that sucker what? The Windy City. Because what you find here is that you get these big wind gusts, right? Gusts of wind. And let me tell you, if you've ever been in a building, maybe I should write the name of this in case you want to go and look. So if you look at the Sears Tower, because of the wind, you can get some huge rockings. And because of these big rockings, you know, gosh, I wish I remember the numbers. I know, if I remember correctly, the Sears Tower at the top would displace something like 30 meters, I believe, in a wind, where it would rock 30 meters to the left, and then it would come all the way to its equilibrium point, and then would rock another 30 meters. Dude, that is huge. But compared to the size of the building, it's not that much. And so what you find here is that in order to stop this rocking, what they do here, down here at the bottom, they have spring dampers. And man, it's a big deal. So if I remember correctly, from what I read here, these dampers on the spring Sears Tower has a spring constant of about 10 to the 9 newtons per meter. So then check this out. That's 1 million newtons in order to stretch this thing out 1 meter. That's a lot.